Imagine a colossal star attempting to engulf a black hole. Sounds like the plot of a sci-fi movie, right? But this scenario may have actually led to a groundbreaking discovery in the field of astronomy. In 2023, scientists observed one of the most remarkable cosmic explosions ever recorded, occurring approximately 750 million light-years away from Earth. This event, which took place on July 7th, was initially classified as a typical supernova, a phenomenon marking the explosive demise of a star, and was designated SN 2023 ZKD. However, 6 months later, further investigations revealed something unusual about this explosion. A search for cosmic anomalies flagged SN 2023 ZKD as peculiar, prompting astronomers to revisit the data collected since its initial detection. To their astonishment, they found that the supernova had brightened once more. This unexpected behavior led to a fascinating hypothesis. The unusual sequence of events might be attributed to a massive star attempting to consume a black hole. Our analysis indicates that the explosion was triggered by a catastrophic encounter with a black hole companion, providing the strongest evidence to date that such close interactions can indeed cause a star to detonate. Explained astronomer Alexander Gagliano from the NSF Institute for Artificial Intelligence and Fundamental Interactions. Supernovae can occur through various mechanisms, typically involving the death of a massive star or runaway thermonuclear explosions on a white dwarf. These cosmic events are relatively common, with hundreds observable each year across the universe. Astronomers generally understand the expected progression of a supernova, a bright flash of light, followed by a gradual dimming that follows a predictable pattern over the following weeks and months. Initially, SN 2023 ZKD appeared to follow this typical pattern, with a flare detected by the Zwicky Transient Facility indicating the early stages of a supernova. However, in January 2024, a specialized tool designed to identify unusual cosmic events flagged this explosion for a second look. Observations from various observatories around the globe had recorded the expected fading light curve. But then, 240 days after its initial discovery, the supernova brightened again, nearly reaching its original luminosity. This behavior is not characteristic of most supernovae, prompting Gagliano and his team to delve into archival observations of that region of the sky. They employed machine learning techniques to uncover signals that might have eluded human detection. Their findings revealed that for over 4 years leading up to the explosion, the object had been gradually brightening, accompanied by some unusual fluctuations. Such long-term behavior is atypical for stars on the verge of exploding. The researchers concluded that the scenario most consistent with their observations involved a massive dying star and a compact object, such as a black hole, locked in a close orbit. As these two celestial bodies spiraled around each other in a decaying orbit, the star lost a significant amount of its mass, which began to emit light. Eventually, the two objects drew close enough that the star's gravitational force attempted to engulf the black hole. However, the immense gravitational pull of the black hole placed such stress on the star that it triggered a supernova. The initial peak in brightness resulted from the supernova's shockwave colliding with low-density gas surrounding the system, while the subsequent peak was due to a slower, sustained interaction with the dense cloud of material expelled by the star in its final years. The strange fluctuations observed prior to the explosion indicated a system under stress from the presence of a black hole. This scenario is not as far-fetched as it may seem. A black hole exerts gravitational force equivalent to that of a star of similar mass. Thus, if you are at a reasonable distance, the gravitational effects are similar. However, because a black hole is so compact, one can get much closer to it than to a star of comparable mass, leading to a unique gravitational experience. For instance, the Sun has a diameter of about 1.4 million kilometers, 865,000 miles, while the event horizon of a black hole with the same mass as the Sun is merely about 6 kilometers across. Therefore, If the star in this binary system had a greater mass than the black hole, it would be seen as the star pulling the black hole in, only for the black hole's intense gravity to ultimately lead to the star's demise. Alternatively, it is also possible that the black hole completely consumed the star before it could explode. Both scenarios would result in a similar interaction with the surrounding material. Regardless of the specifics, the outcome is a larger black hole. We are now entering a new era where we can automatically detect these rare events as they occur rather than only after the fact, Gagliano remarked. This advancement allows us to begin connecting the dots between the life cycle of a star and its eventual death, which is incredibly exciting. This groundbreaking research is set to be published in the Astrophysical Journal, with a preprint available on arXiv.